All right. So continuing on our last discussion here, we were talking here about the curvature of space. So depending on the density of the universe, very early on, the universe could be spherical, flat, or hyperbolic. Spherical is a closed universe. You go in one direction forever, you end up at the starting point. So this is like the surface of the earth. You go east far enough and you find out you're back where you started, because you never turn around, never go the other direction, but you circumnavigate the world. Now the difference is, in the universe, to do that will take twice the age of the universe, and the universe is always expanding, so it'll always be longer than the age of the universe. You couldn't really do that, but in principle it would suggest that if you're standing in the universe and you look in one direction, the farthest thing that you can see, and then turn and look in the other direction, the farthest you can see in that direction, you're seeing the same spot. So the edge of the universe in all directions is the same spot that you are, just expanded out there. And so again, the actual way of thinking about this is kind of complicated, and I kind of wish we had more time to cover it this semester, but with the coronavirus, sort of way of putting all this class online, we kind of are missing out on a little bit of our really cool discussions to go with this. Hyperbolic space, gravity's never strong enough to slow down the expansion of the universe. The universe expands forever, never quite slowing down, and just expands basically into nothingness. Everything gets too far apart. And again, for theorists, that was a very uncomfortable thing, because it made the universe have a beginning but no end, and mathematically that's very difficult to deal with. A spherical universe that has a beginning and an end, well, we already talked about virtual particles coming and going into the universe, so they were talking about the possibility that we have two universes that came into being, like a universe and an anti-universe, and they are both temporary. And so that that was a really cool idea for theorists to think about. Flat space, just statistically, that just shouldn't happen at all. But all the measurements kept coming up flat, and that was like really problematic, because that was even worse than an open universe, or a hyperbolic universe. And so the Hubble telescope was supposed to solve all the problem. We're going to figure all this out. The universe seemed too flat, but they thought if we looked really, really, really far away, we would see that the universe was expanding a little bit faster back then, and we could measure the rate of deceleration, and that would tell us basically how much mass was in the early universe. Would solve the problem, and everybody would be happy. Problem was, it's not what they found. The problem is, 1998, I was at a meeting of the American Astronomical Society. It was actually in Austin, Texas that year. And they presented the results of two different studies. Now, neither group of astronomers knew the other one was working on that project until like shortly before the meeting. And they were both looking at the most distant objects. Type 1a supernova. These are so bright you can see them from like near the edge of the universe. And so they were finding the most distant supernovae and figuring out the expansion rates of the universe. And the anticipation was the universe was slowing down at a particular rate. What they discovered, however, was it was slowing down wrong and then speeding up. Yeah, the universe started off expanding like they expected, started slowing because gravity would be slowing it, and then started speeding up again. So what we now realize is that for the last several billion years, the universe has been actually expanding rapidly, more rapidly. And so it's been accelerating the expansion. And this was like a total complete shock. This was not at all what they expected. This is what nobody expected. So they looked at the most distant supernovae, and sure enough, other groups looked at their data and said, they're right. So Saul Perlmutter and Brian Schmidt discovered that the universe is expanding, and it's accelerating expansion, as if something is pushing outwards. Well, what could be doing that? Well, they realized, go back to what Einstein did with the Friedman equation. He stuck that extra term in there to balance the universe. If the extra term is exactly right, it balances the universe, you get a static universe. But they realized, wait a minute, that term could be something else rather than just right. You could still have that term in there because mathematically nothing prohibited that term being there. But that would be an outward push. Now Einstein stuck it in there to be an outward push to balance the pull of gravity. Well, they realized it might overbalance, in which case it's an outward push in the universe. So the universe expands, gravity slows it down, but once it gets big enough, because that term is constant, and that's the thing, it's a constant. So the bigger the universe is, the more space there is. The more space there is, the more outward it pushes. And so at some point, that outward push overcomes gravity, and now the universe starts speeding up. So that means a non-zero cosmological constant. So that means the universe keeps expanding and will keep expanding forever, just going faster and faster and faster, not slowing down like they thought. They just thought it wouldn't slow down enough. Now they realize it's going to speed up forever and ever and ever until eventually it kind of rips itself apart. So now instead of having a big crunch, they talk about something called the big rip. Okay. So as the universe expands, you have extra dark matter, stuff that we don't know what it is, which is slowing the universe. And because there's all this extra matter, extra gravity. Well, by analogy, the outward push they started referring to as dark energy. Now, it's not really a great name for it, but that's the name they came up with because we had dark matter pulling inward, dark energy pushing outward. Okay, so what is dark energy? Is it really energy? Because that's actually my contention is that this is a bad name for it. Because dark energy is constant; it has a constant density. That means the more space you have, the more dark energy you have. If you got twice as much space, you get twice as much dark energy. Well, that's not conserved. The universe is expanding, so that means dark energy keeps increasing, and so that means more and more of it. It means it accelerates faster and faster because there's more and more of it, but it also means it's not conserved. That means it's not energy, not as we know energy. So the universe cannot be energy as we define energy. It's got to be something else. Kind of like dark matter is something weird that's not like ordinary matter, but at least it acts with gravity, so it acts like matter. And it probably is some kind of matter, but not anything normal that we recognize. Dark energy, well, that's not really sure what this dark energy is, and there's like all kinds of ideas about dark energy. What is this dark energy? Every now and then there's something in the news about some experiment that's supposed to find what dark matter is, and they're going to measure dark matter and solve the problem. Well, it turns out they keep not solving the problem because they keep not finding what the dark matter is. And likewise, dark energy, there's been all kind of studies to try to figure out what it is, and they can't figure it out. There's been some theorists saying, it's like some higher dimensions of space, energy leaking from higher dimensions, maybe another universe interacting with ours, maybe all kinds of other things. There's maybe even our observations are wrong and it's not really there. Maybe there's an extra force that we don't know about that's making it. There's lots and lots of ideas. None of them have been proven. None of them have actually even survived any tests they've made for them. So you may see and read a lot on the internet about dark energy. Most of that is just, in fact, virtually all of that is just pure speculation because we honestly don't know what this dark energy stuff is. We don't know. We do know it's pushing outwards though, and so. That makes it kind of interesting. Now in science fiction, it's like really cool because that means that you can talk about space itself as having energy that's undepletable, and so it can push on things and do work, and so you can have an energy source that's completely inexhaustible. Again, that violates several laws of physics, so I don't really think that such a device would really work. But it is kind of a cool thing, and again, being a sci-fi nerd, okay, I know I normally do Star Trek references, but this is a Stargate reference, because in the Stargate universe, they had these aliens called the Ancients who had figured out a way of tapping into this inexhaustible energy supply of space, what they call 0 point energy. And so, but anyway, it's probably something that cannot really be done. Dark energy is uniformly distributed around the universe, and so that means that it's everywhere, but it is entirely a tiny little amount. Imagine energy, E equals mc squared. And so if you take the amount of energy and divide by c squared, it gives you the equivalent amount of mass that's there. And dark energy has this unbelievably tiny density that is so incredibly tiny, it is virtually impossible to measure. And in fact, we've been unable to measure it really anywhere on Earth, which also makes a little tabletop 0 point energy device like totally worthless. But anyway, but it does make the energy very hard to measure. It takes a huge amount of space for it to add up to anything. So that means the dark energy, in a room doesn't account for anything. Dark energy, even within a solar system, is not enough. It's not big enough to count for, even as big as a solar system is. Even within a galaxy, the dark energy in a galaxy is pretty small compared to everything else in the galaxy, like the gravity. It takes millions of light years worth of space for dark energy to really add up to anything like